Section 2 of the Outline of Science, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by J.C. Guan. The Outline of Science, Volume 1, by J. Arthur Thomson. Section 2. Part 1. The Romance of the Heavens. Continued. Is there life on Mars? The basis of this belief is that if, as we saw, all the globes in our solar system are masses of metal that are cooling down, the smaller will have cooled down before the larger, and will be further ahead in their development. Now Mars is very much smaller than the Earth, and must have cooled at its surface millions of years before the Earth did. Hence, if a story of life began on Mars at all, it began long before the story of life on the Earth. We cannot guess what sort of life forms would be evolved in a different world, but we can confidently say that they would tend toward increasing intelligence, and thus we are disposed to look for highly intelligent beings on Mars. But this argument supposes that the conditions of life, namely air and water, are found on Mars, and it is disputed whether they are found there in sufficient quantity. The late Professor Percival Lowell, who made a lifelong study of Mars, maintained that there are hundreds of straight lines drawn across the surface of the planet, and he claimed that they are beds of vegetation marking the sites of great channels, or pipes, by means of which the Martians draw water from the polar ocean. Professor W.H. Pickering, another high authority, thinks that the lines are long, narrow marshes fed by moist winds from the poles. There are certainly white polar caps on Mars. They seem to melt in the spring, and the dark fringe around them grows broader. Other astronomers, however, say that they find no trace of water vapor in the atmosphere of Mars, and they think that the polar caps may be simply thin sheets of hoar-frost or frozen gas. They point out that, as the atmosphere of Mars is certainly scanty, and the distance from the sun is so great, it may be too cold for the fluid water to exist on the planet. If one asks why our wonderful instruments cannot settle these points, one must be reminded that Mars is never nearer than 34 million miles from the Earth, and only approaches this distance once in 15 or 17 years. The image of Mars on the photographic negative taken in a big telescope is very small. Astronomers rely to a great extent on the eye, which is more sensitive than the photographic plate. But it is easy to have differences of opinion as to what the eye sees, and so there is a good deal of controversy. In August 1924 the planet will again be well placed for observation, and we may learn more about it. Already a few of the much disputed lines, which people wrongly call canals, have been traced on photographs. Astronomers who are skeptical about life on Mars are often not fully aware of the extraordinary adaptability of life. There was a time when the climate of the whole earth, from pole to pole, was semi-tropical for millions of years. No animal could then endure the least cold, yet now we have plenty of arctic plants and animals. If the cold came slowly on Mars, as we have reason to suppose, the population could be gradually adapted to it. On the whole, it is possible that there is advanced life on Mars, and it is not impossible, in spite of the very great difficulties of a code of communication, that our elder brothers may yet flash across space the solution of many of our problems. Part 2. Jupiter and Saturn. Next to Mars, going outward from the sun, is Jupiter. Between Mars and Jupiter, however, there are more than 300 million miles of space, and the older astronomers wondered why this was not occupied by a planet. We now know that it contains about 900 planetoids, or small globes, of from 5 to 500 miles in diameter. It was at one time thought that a planet might have burst into these fragments, a theory which is not mathematically satisfactory; or it may be that the material which is gathered in them was prevented by the nearness of the great bulk of Jupiter from uniting into one globe. For Jupiter is a giant planet, and its gravitational influence must extend far over space. It is 1,300 times as large as the earth, and has 9 moons, 4 of which are large in attendance on it. It is interesting to note that the outermost moons of Jupiter and Saturn revolve round these planets in a direction contrary to the usual direction taken by moons round planets, and by planets round the sun. But there is no life on Jupiter. The surface which we see in photographs is a mass of cloud or steam which always envelops the body of the planet. It is apparently red hot. A red tinge is seen sometimes at the edges of its cloud belts, and a large red region, the red spot, 33,000 miles in length, has been visible on it for half a century. There may be a liquid or solid core to the planet, but as a whole it is a mass of seething vapors whirling round on its axis once in every 10 hours. As in the case of the sun, however, different latitudes appear to rotate at different rates. The interior of Jupiter is very hot, but the planet is not self-luminous. The planets Venus and Jupiter shine very brightly, but they have no light of their own. They reflect the sunlight. Saturn is in the same interesting condition. The surface is steam, and Saturn is so far away from the sun that the vaporization of its oceans must necessarily be due to its own internal heat. It is too hot for water to settle on its surface. Like Jupiter, the great globe turns on its axis once in 10 hours, a prodigious speed, and must be a swirling, seething mass of metallic vapors and gases. It is instructive to compare Jupiter and Saturn in this respect with the sun. They are smaller globes, and have cooled down more than the central fire. Saturn is a beautiful object in the telescope because it has 10 moons, to include one which is disputed, and a wonderful system of rings round it. The so-called rings are a mighty swarm of meteorites, pieces of iron and stone of all sorts and sizes, which reflect the light of the sun to us. This ocean of matter is some miles deep, and stretches from a few thousand miles from the surface of the planet to 172,000 miles out in space. Some astronomers think that this is volcanic material which has been shot out of the planet. Others regard it as stuff which would have combined to form an 11th moon, but was prevented by the nearness of Saturn itself. There is no evidence of life on Saturn. The Moon. Mars and Venus are therefore the only planets, besides the earth, on which we may look for life, and in the case of Venus the possibility is very faint. But what about the moons which attend the planets? They range in size from the little 10 miles wide moons of Mars to Titan, a moon of Saturn, and Ganymede, a satellite of Jupiter, which are about 3,000 miles in diameter. May there not be life on some of the larger of these moons? We will take our own moon as a type of the class. A dead world. The moon is so very much nearer to us than any other heavenly body that we have a remarkable knowledge of it. In Fig. 14 you have a photograph taken in one of our largest telescopes of part of its surface. In a sense, such a telescope brings the moon to within about 50 miles of us. We should see a city like London as a dark, sprawling blotch on the globe. We could just detect a Zeppelin or a Diplodocus as a moving speck against the surface. But we find none of these things. It is true that a few astronomers believe that they see signs of some sort of feeble life or movement on the moon. Professor Pickering thinks that he can trace some volcanic activity. He believes that there are areas of vegetation, probably of a low order, and that the soil of the moon may retain a certain amount of water in it. He speaks of a very thin atmosphere, and of occasional light falls of snow. He has succeeded in persuading some careful observers that there probably are slight changes of some kind taking place on the moon. But there are many things that point to absence of air on the moon. Even the photographs we reproduce tell the same story. The edges of the shadows are all hard and black. If there had been an appreciable atmosphere, it would have scattered the sun's light on to the edges and produced a gradual shading off, such as we see on the earth. This relative absence of air must give rise to some surprising effects. There will be no sounds on the moon, because sounds are merely air waves. Even a meteor shattering itself to a violent end against the surface of the moon would make no noise, nor would it herald its coming by glowing into a shooting star, as it would on entering the earth's atmosphere. There will be no floating dust, no scent, no twilight, no blue sky, no twinkling of the stars. The sky will be always black, and the stars will be clearly visible by day as by night. The sun's wonderful corona, which no man on earth, even by seizing every opportunity during eclipses, can hope to see for more than 2 hours in all a long lifetime, will be visible all day. So will the great red flames of the sun. Of course, there will be no life, and no landscape effects and scenery effects due to vegetation. The moon takes approximately 27 of our days to turn once on its axis. So for 14 days there is continuous night, when the temperature must sink away down towards the absolute cold of space. This will be followed without an instant of twilight by full daylight. For another 14 days the sun's rays will bear straight down, with no diffusion or absorption of their heat or light on the way. It does not follow, however, that the temperature of the moon's surface must rise enormously. It may not even rise to the temperature of melting ice. Seeing there is no air, there can be no check on radiation. The heat that the moon gets will radiate away immediately. We know that amongst the coldest places on the earth are the tops of very high mountains, the points that have reared themselves nearest to the sun but furthest out of the sheltering blanket of the earth's atmosphere. The actual temperature of the moon's surface by day is a moot point. It may be below the freezing point or above the boiling point of water. The mountains of the moon. The lack of air is considered by many astronomers to furnish the explanation of the enormous number of craters which pit the moon's surface. There are about 100,000 of these strange rings, and it is now believed by many that they are spots where very large meteorites, or even planetoids, splashed into the moon when its surface was still soft. Other astronomers think that they are the remains of gigantic bubbles, which were raised in the moon's skin, when the globe was still molten, by volcanic gases from below. A few astronomers think that they are, as is popularly supposed, the craters of extinct volcanoes. Our craters on the earth are generally deep cups, whereas these ring formations on the moon are more like very shallow and broad saucers. Clavius, the largest of them, is 123 miles across the interior, yet its encircling rampart is not a mile high. The mountains on the moon rise to a great height, and are extraordinarily gaunt and rugged. They are like fountains of lava, rising in places to 26,000 and 27,000 feet. The lunar Apennines have 3,000 steep and weird peaks. Our terrestrial mountains are continually worn down by the frost acting on moisture, and by ice and water, but there are none of these agencies operating on the moon. Its mountains are comparatively everlasting hills. The moon is interesting to us, precisely because it is a dead world. It seems to show how the earth, or any cooling metal globe, will evolve in the remote future. We do not know if there was ever life on the moon, but in any case it cannot have proceeded far in development. At the most we can imagine some strange lowly forms of vegetation lingering here and there in pools of heavy gas, expanding during the blaze of the sun's long day, and frozen rigid during the long night. Meteors and comets. We may conclude our survey of the solar system with a word about shooting stars, or meteors, and comets. There are few now who do not know that the streak of fire which suddenly lights the sky overhead at night means that a piece of stone or iron has entered our atmosphere from outer space, and has been burned up by friction. It was travelling at perhaps 20 or 30 miles a second. At 70 or 80 miles above our heads it began to glow, and at that height the air is thick enough to offer serious friction and raise it to a white heat. By the time the meteor reached about 20 miles or so from the earth's surface it was entirely dissipated, as a rule in fiery vapor. Millions of meteorites. It is estimated that between 10 and 100 million meteorites enter our atmosphere and are cremated every day. Most of them weigh only an ounce or two, and are invisible. Some of them weigh a ton or more, but even against these large masses the air acts as a kind of torpedo net. They generally burst into fragments and fall without doing damage. It is clear that empty space is, at least within the limits of our solar system, full of these things. They swarm like fishes in the seas. Like the fishes, moreover, they may be either solitary or gregarious. The solitary bit of cosmic rubbish is the meteorite, which we have just examined. A social group of meteorites is the essential part of a comet. The nucleus, or bright central part, of the head of a comet consists of a swarm, sometimes thousands of miles wide, of these pieces of iron or stone. This swarm has come under the sun's gravitational influence, and is forced to travel round it. From some dark region of space it has moved slowly into our system. It is not then a comet, for it has no tail, but as the crowded meteors approach the sun the speed increases. They give off fine vapor-like matter, and the fierce flood of light from the sun sweeps this vapor out in an ever-lengthening tail. Whatever way the comet is travelling, the tail always points away from the sun. A great comet. The vapory tail often grows to an enormous length as the comet approaches the sun. The great comet of 1843 had a tail 200 million miles long. It is, however, composed of the thinnest vapors imaginable. Twice during the 19th century the earth passed through the tail of a comet, and nothing was felt. The vapors of the tail are, in fact, so attenuated that we can hardly imagine them to be white-hot. They may be lit by some electrical force. However that may be, the comet dashes round the sun, often at 300 or 400 miles a second, then may pass gradually out of our system once more. It may be 1,000 years, or it may be 50 years, before the monarch of the system will summon it again to make its fiery journey round his throne. The Stellar Universe. Part 1. The immensity of the stellar universe, as we have seen, is beyond our apprehension. The sun is nothing more than a very ordinary star, perhaps an insignificant one. There are stars enormously greater than the sun. One such, Betelgeuse, has recently been measured, and its diameter is more than 300 times that of the sun. The evolution of stars. The proof of the similarity between our sun and the stars has come to us through the spectroscope. The elements that we find by its means in the sun are also found in the same way in the stars. Matter, says the spectroscope, is essentially the same everywhere, in the earth and the sun, in the comet that visits us once in 1,000 years, in the star whose distance is incalculable, and in the great clouds of fire mist that we call nebulae. In considering the evolution of the stars, let us keep 2 points clearly in mind. The starting point, the nebula, is no figment of the scientific imagination. Hundreds of thousands of nebulae, besides even vaster irregular stretches of nebulous matter, exist in the heavens. But the stages of the evolution of this stuff into stars are very largely a matter of speculation. Possibly there is more than one line of evolution, and the various theories may be reconciled. And this applies also to the theories of the various stages through which the stars themselves pass on their way to extinction. The light of about 250,000 stars has been analyzed in the spectroscope, and it is found that they fall into about a dozen classes, which generally correspond to stages in their evolution. The age of stars. In its main lines, the spectrum of a star corresponds to its color, and we may roughly group the stars into red, yellow, and white. This is also the order of increasing temperature, the red stars being the coolest, and the white stars the hottest. We might therefore imagine that the white stars are the youngest, and that as they grow older and cooler, they become yellowish, then red, and finally become invisible, just as a cooling white-hot iron would do. But a very interesting recent research shows that there are 2 kinds of red stars. Some of them are amongst the oldest stars, and some are amongst the youngest. The facts appear to be that when a star is first formed, it is not very hot. It is an immense mass of diffuse gas glowing with a dull red heat. It contracts under the mutual gravitation of its particles, and as it does so, it grows hotter. It acquires a yellowish tinge. As it continues to contract, it grows hotter and hotter, until its temperature reaches a maximum as a white star. At this point, the contraction process does not stop, but the heating process does. Further contraction is now accompanied by cooling, and the star goes through its color changes again, but this time in the inverse order. It contracts and cools to a yellow, and finally to red. But when it again becomes a red star, it is enormously denser and smaller than when it began as a red star. Consequently, the red stars are divided into 2 classes, called, appropriately, giants and dwarfs. This theory, which we owe to an American astronomer, H.N. Russell, has been successful in explaining a variety of phenomena, and there is consequently good reason to suppose it to be true. But the question as to how the red giant stars are formed has received less satisfactory and precise answers. The most commonly accepted theory is the nebular theory. The nebular theory. Part 2. Nebulae are dim, luminous cloud-like patches in the heavens, more like wisps of smoke in some cases than anything else. Both photography and the telescope show that they are very numerous, hundreds of thousands being already known, and the number being continually added to. They are not small. Most of them are immensely large. Actual dimensions cannot be given, because to estimate these we must first know definitely the distance of the nebulae from the earth. The distances of some nebulae are known approximately, and we can therefore form some idea of size in these cases. The results are staggering. The mere visible surface of some nebulae is so large that the whole stretch of the solar system would be too small to form a convenient unit for measuring it. A ray of light would require to travel for years to cross from side to side of such a nebula. Its immensity is inconceivable to the human mind. There appear to be two types of nebula, and there is evidence suggesting that the one type is only an earlier form of the other, but this again we do not know. The more primitive nebulae would seem to be composed of gas in an extremely rarefied form. It is difficult to convey an adequate idea of the rarity of nebular gases. The residual gases in a vacuum tube are dense by comparison. A cubic inch of air at ordinary pressure would contain more matter than is contained in millions of cubic inches of the gases of nebulae. The light of even the faintest stars does not seem to be dimmed by passing through a gaseous nebula, although we cannot be sure on this point. The most remarkable physical fact about these gases is that they are luminous. Whence they derive their luminosity we do not know. It hardly seems possible to believe that extremely thin gases exposed to the terrific cold of space can be so hot as to be luminous and can retain their heat and their luminosity indefinitely. A cold luminosity due to electrification, like that of the aurora borealis, would seem to fit the case better. Now the nebular theory is that out of the great fire mists, such as we have described, stars are born. We do not know whether gravitation is the only or even the main force at work in a nebula, but it is supposed that under the action of gravity the far-flung fire mists would begin to condense round centres of greatest density, heat being evolved in the process. Of course the condensation would be enormously slow, although the sudden eruption of a swarm of meteors or some solid body might hasten matters greatly by providing large, ready-made centres of condensation. Spiral nebulae. It is then supposed that the contracting mass of gas would begin to rotate and throw off gigantic streamers, which would, in their turn, form centres of condensation. The whole structure would thus form a spiral, having a dense region at its centre, and knots or lumps of condensed matter along its spiral arms. Besides the formless gaseous nebulae, there are hundreds of thousands of spiral nebulae, such as we have just mentioned, in the heavens. They are at all stages of development, and they are visible to us at all angles. That is to say, some of them face directly towards us, others are edge-on, and some are in intermediate positions. It appears, therefore, that we have here a striking confirmation of the nebular hypothesis. But we must not go so fast. There is some controversy as to the nature of these spiral nebulae. Some eminent astronomers think they are other stellar universes, comparable in size with our own. In any case, they are vast structures, and if they represent stars in process of condensation, they must be giving birth to huge agglomerations of stars, to star clusters at least. These vast and enigmatic objects do not throw much light on the origin of our own solar system. The nebular hypothesis, which was invented by Laplace to explain the origin of our solar system, has not yet met with universal acceptance. The explanation offers grave difficulties, and it is best, while the subject is still being closely investigated, to hold all opinions with reserve. It may be taken as probable, however, that the universe has developed from masses of incandescent gas. The Birth and Death of Stars. Part 3. Variable, new, and dark stars. Dying suns. Many astronomers believe that in variable stars we have another star, following that of the dullest red star, in the dying of suns. The light of these stars varies periodically in so many days, weeks, or years. It is interesting to speculate that they are slowly dying suns, in which the molten interior periodically bursts through the shell of thick vapours that is gathering round them. What we saw about our sun seems to point to some such stage in the future. That is, however, not the received opinion about variable stars. It may be that they are stars which periodically pass through a great swarm of meteors, or a region of space that is rich in cosmic dust of some sort, when of course a great illumination would take place. One class of these variable stars, which takes its name from the star Algol, is of special interest. Every third night Algol has its light reduced for several hours. Modern astronomy has discovered that in this case there are really two stars, circulating round a common centre, and that every third night the fainter of the two comes directly between us and its companion, and causes an eclipse. This was until recently regarded as a most interesting case in which a dead star revealed itself to us by passing before the light of another star. But astronomers have in recent years invented something, the selenium cell, which is even more sensitive than the photographic plate, and on this the supposed dead star registers itself as very much alive. Algol is, however, interesting in another way. The pair of stars which we have discovered in it are hundreds of trillions of miles away from the earth, yet we know their masses and their distances from each other. The death and birth of stars. We have no positive knowledge of dead stars, which is not surprising when we reflect that a dead star means an invisible star. But when we see so many individual stars tending toward death, when we behold a vast population of all conceivable ages, we presume that there are many already dead. On the other hand, there is no reason to suppose that the universe as a whole is running down. Some writers have maintained this, but their argument implies that we know a great deal more about the universe than we actually do. The scientific man does not know whether the universe is finite or infinite, temporal or eternal, and he declines to speculate where there are no facts to guide him. He knows only that the great gaseous nebula promise myriads of worlds in the future, and he concedes the possibility that new nebulae may be forming in the ether of space. The last and not the least interesting subject we have to notice is the birth of a new star. This is an event which astronomers now announce every few years, and it is a far more portentous event than the reader imagines when it is reported in his daily paper. The story is much the same in all cases. We say that the star appeared in 1901, but you begin to realize the magnitude of the event when you learn that this distant blaze had really occurred about the time of the death of Luther. The light of the conflagration had been speeding toward us across space at 186,000 miles a second, yet it has taken nearly 3 centuries to reach us. To be visible at all to us at that distance, the fiery outbreak must have been stupendous. If a mass of petroleum 10 times the size of the earth were suddenly fired, it would not be seen at such a distance. The new star had increased its light many hundredfold in a few days. There is a considerable fascination about the speculation that in such cases we see the resurrection of a dead world, a means of renewing the population of the universe. What happens is that in some region of the sky where no star, or only a very faint star, had been registered on our charts, we almost suddenly perceive a bright star. In a few days it may rise to the highest brilliancy. By the spectroscope we learn that this distant blaze means a prodigious outpour of white-hot hydrogen at hundreds of miles a second. But the star sinks again after a few months, and we then find a nebula round it on every side. It is natural to suppose that a dead or dying sun has somehow been reconverted in whole or in part into a nebula. A few astronomers think that it may have partially collided with another star, or approached too closely to another, with the result we described in an earlier page. The general opinion now is that a faint or dead star had rushed into one of those regions of space in which there are immense stretches of nebulous matter, and been, at least in part, vaporized by the friction. But the difficulties are considerable, and some astronomers prefer to think that the blazing star may merely have lit up a dark nebula which already existed. It is one of those problems on which speculation is most tempting, but positive knowledge is still very incomplete. We may be content, even proud, that already we can take a conflagration that has occurred more than 1,000 trillion miles away and analyze it positively into an outflame of glowing hydrogen gas at so many miles a second. The shape of our universe. Part 4. Our universe, a spiral nebula. What is the shape of our universe, and what are its dimensions? This is a tremendous question to ask. It is like asking an intelligent insect, living on a single leaf in the midst of a great Brazilian forest, to say what is the shape and size of the forest. Yet immense ingenuity has proved equal to giving an answer even to this question, and by a method exactly similar to that which would be adopted by the insect. Suppose, for instance, that the forest was shaped as an elongated oval, and the insect lived on a tree near the center of the oval. If the trees were approximately equally spaced from one another, they would appear much denser along the length of the oval than across its width. This is the simple consideration that has guided astronomers in determining the shape of our stellar universe. There is one direction in the heavens along which the stars appear denser than in the directions at right angles to it. That direction is the direction in which we look towards the Milky Way. If we count the number of stars visible all over the heavens, we find they become more and more numerous as we approach the Milky Way. As we go further and further from the Milky Way, the stars thin out until they reach a maximum sparseness in directions at right angles to the plane of the Milky Way. We may consider the Milky Way to form, as it were, the equator of our system, and the line at right angles to point to the north and south poles. Our system, in fact, is shaped something like a lens, and our sun is situated near the center of this lens. In the remoter part of this lens, near its edge, or possibly outside it altogether, lies the great series of star clouds which make up the Milky Way. All the stars are in motion within this system, but the very remarkable discovery has been made that these motions are not entirely random. The great majority of the stars whose motions can be measured fall into two groups drifting past one another in opposite directions. The velocity of one stream relative to the other is about 25 miles per second. The stars forming these two groups are thoroughly well mixed. It is not a case of an inner stream going one way and an outer stream the other. But there are not quite as many stars going one way as the other. For every 2 stars in one stream there are 3 in the other. Now, as we have said, some eminent astronomers hold that the spiral nebulae are universes like our own. These spirals present features which, in the light of what we have just said about our system, are very remarkable. The nebula in Coma Berenices is a spiral edge-on to us, and it has precisely the lance-shaped middle and the general flattened shape that we have found in our own system. The nebula in Canis Venatici is a spiral facing towards us, and its shape irresistibly suggests motions along the spiral arms. This motion, whether it is towards or away from the central, lance-shaped portion, would cause a double streaming motion in that central portion of the kind we have found in our own system. Again, and altogether apart from these considerations, there are good reasons for supposing our Milky Way to possess a double-armed spiral structure. and the great patches of dark, absorbing matter which are known to exist in the Milky Way would give very much the mottled appearance we notice in the arms, which we see edge on, of the nebula in Coma Berenices. The hypothesis, therefore, that our universe is a spiral nebula has much to be said for it. If it be accepted, it greatly increases our estimate of the size of the material universe. For our central, lens-shaped system is calculated to extend towards the Milky Way for more than 20,000 times a million miles, and about a third of this distance towards what we have called the poles. If, as we suppose, each spiral nebula is an independent stellar universe comparable in size with our own, then, since there are hundreds of thousands of spiral nebulae, we see that the size of the whole material universe is indeed beyond our comprehension. Astronomical Instruments. Part 1. The Telescope. The instruments used in modern astronomy are almost the finest triumphs of mechanical skill in the world. In a great modern observatory the different instruments are to be counted by the score, but there are two which stand out preeminent as the fundamental instruments of modern astronomy. These instruments are the telescope and the spectroscope, and without them astronomy, as we know it, could not exist. There is still some dispute as to where and when the first telescope was constructed. As an astronomical instrument, however, it dates from the time of the great Italian scientist Galileo, which, with a very small and imperfect telescope of his own invention, first observed the spots on the sun, the mountains of the moon, and the chief four satellites of Jupiter. A good pair of modern binoculars is superior to this early instrument of Galileo's, and the history of telescope construction, from that primitive instrument to the modern giant recently erected on Mount Wilson, California, is an exciting chapter in human progress. But the early instruments have only an historic interest. The era of modern telescopes began in the 19th century. During the last century, telescope construction underwent an unprecedented development. An immense amount of interest was taken in the construction of large telescopes, and the different countries of the world entered on an exciting race to produce the most powerful possible instruments. Besides this rivalry of different countries, there was a rivalry of methods. The telescope developed along two different lines, and each of these two types has its partisans at the present day. These types are known as refractors and reflectors, and it is necessary to mention briefly the principles employed in each. The refractor is the ordinary, familiar type of telescope. It consists essentially of a large lens at one end of a tube, and a small lens, called the eyepiece, at the other. The function of the large lens is to act as a sort of gigantic eye. It collects a large amount of light, an amount proportional to its size, and brings this light to a focus within the tube of the telescope. It thus produces a small but bright image, and the eyepiece magnifies this image. In the reflector, instead of a large lens at the top of the tube, a large mirror is placed at the bottom. This mirror is so shaped as to reflect the light that falls on it to a focus, whence the light is again led to an eyepiece. Thus the refractor and the reflector differ chiefly in their manner of gathering light. The powerfulness of the telescope depends on the size of the light gatherer. A telescope with a lens 4 inches in diameter is 4 times as powerful as the one with a lens of 2 inches in diameter, for the amount of light gathered obviously depends on the area of the lens, and the area varies as the square of the diameter. The largest telescopes at present in existence are reflectors. It is much easier to construct a very large mirror than to construct a very large lens. It is also cheaper. A mirror is more likely to get out of order than is a lens, however, and any irregularity in the shape of a mirror produces a greater distorting effect than in a lens. A refractor is also more convenient to handle than is a reflector. For these reasons, great refractors are still made, but the largest of them, the Great Yerkes refractor, is much smaller than the greatest reflector, the one on Mount Wilson, California. The lens of the Yerkes refractor measures 3 feet 4 inches in diameter, whereas the Mount Wilson reflector has a diameter of no less than 8 feet 4 inches. But there is a device whereby the power of these giant instruments, great as it is, can be still further heightened. That device is the simple one of allowing the photographic plate to take the place of the human eye. Nowadays an astronomer seldom spends the night with his eye glued to the great telescope. He puts a photographic plate there. The photographic plate has this advantage over the eye, that it builds up impressions. However long we stare at an object too faint to be seen, we shall never see it. With the photographic plate, however, faint impressions go on accumulating. As hour after hour passes, the star which was too faint to make a perceptible impression on the plate goes on affecting it until finally it makes an impression which can be made visible. In this way the photographic plate reveals to us phenomena in the heavens which cannot be seen through the most powerful telescopes. Telescopes of the kind we have been discussing, telescopes for exploring the heavens, are mounted equatorially. That is to say, they are mounted on an inclined pillar parallel to the axis of the earth, so that, by rotating round this pillar, the telescope is enabled to follow the apparent motion of a star due to the rotation of the earth. This motion is effected by clockwork, so that, once adjusted on the star, and the clockwork started, the telescope remains adjusted on that star for any length of time that is desired. But a great official observatory, such as Greenwich Observatory or the observatory at Paris, has also transit instruments, or telescopes smaller than the equatorials and without the same facility of movement, but which, by a number of exquisite refinements, are more adapted to accurate measurements. It is these instruments which are chiefly used in the compilation of the Nautical Almanac. They do not follow the apparent motion of the stars. Stars are allowed to drift across the field of vision, and as each star crosses a small group of parallel wires in the eyepiece, its precise time of passage is recorded. Owing to their relative fixity of position, these instruments can be constructed to record the positions of stars with much greater accuracy than is possible to the more general and flexible mounting of equatorials. The recording of transit is comparatively dry work. The spectacular element is entirely absent. Stars are treated merely as mathematical points. But these observations furnish the very basis of modern mathematical astronomy, and without them such publications as the Nautical Almanac and the Connaissance du Temps would be robbed of the greater part of their importance. Part II. The Spectroscope. We have already learnt something of the principles of the spectroscope, the instrument which, by making it possible to learn the actual constitution of the stars, has added a vast new domain to astronomy. In the simplest form of this instrument, the analyzing portion consists of a single prism. Unless the prism is very large, however, only a small degree of dispersion is obtained. It is obviously desirable for accurate analytical work that the dispersion, that is, the separation of the different parts of the spectrum, should be as great as possible. The dispersion can be increased by using a large number of prisms, the light emerging from the first prism, entering the second, and so on. In this way, each prism produces its own dispersive effect, and when a number of prisms are employed, the final dispersion is considerable. A considerable amount of light is absorbed in this way, however, so that, unless our primary source of light is very strong, the final spectrum will be very feeble and hard to decipher. Another way of obtaining considerable dispersion is by using a diffraction grating instead of a prism. This consists generally of a piece of glass on which lines are ruled by a diamond point. When the lines are sufficiently close together, they split up light falling on them into its constituents and produce a spectrum. The modern diffraction grating is a truly wonderful piece of work. It contains several thousands of lines to the inch, and these lines have to be spaced with the greatest accuracy. But in this instrument, again, there is a considerable loss of light. We have said that every substance has its own distinctive spectrum, and it might be thought that, when a list of spectra of different substances has been prepared, spectrum analysis would become perfectly straightforward. In practice, however, things are not quite so simple. The spectrum emitted by a substance is influenced by a variety of conditions. The pressure, the temperature, the state of motion of the object we are observing, all make a difference, and one of the most laborious tasks of the modern spectroscopist is to disentangle these effects from one another. Simple as it is in its broad outlines, spectroscopy is, in reality, one of the most intricate branches of modern science. End of section 2.